All right, now we want to look at how we can calculate the probabilities using CDFs. Calculating probabilities with CDFs. So one theorem here, we can say that let X be a random variable with CDF capital F of X. Then we can say that the probability that X is between A and B, meaning that X is bigger than A, less than or equal to B, this can be written as capital F of B minus capital F of A. So this theorem is valid whether X is a discrete random variable or a continuous random variable. In the case of continuous random variable, we saw that it doesn't matter whether we say X is bigger than A or bigger than equal to A, or less than B or less than equal to B, because we saw that probability that X equals a number is always 0. So it doesn't matter whether we add a 0 or not. But in the case of discrete, it matters whether you say bigger than A or bigger than or equal to A. So here, the correct statement is X bigger than A, less than or equal to B. That can be written as F of B minus F of A. So let's see why. Proof. Note that this event here, X bigger than A, less than or equal to B, can be written as the event X less than equal to B minus X less than equal to A. Because what is the meaning of X bigger than A less than equal to B? So that means X is less than equal to B, and maybe I can justify this way. See, this is same as X less than equal to B, and X is not less than equal to A. When you say that a number is between, for example, 5 to 10, bigger than 5, less than equal to 10. It's same as saying that the number is less than equal to 10 and it's not less than equal to 5. If the number is not less than equal to A, it means that it must be bigger than A. This intersection means and X less than equal to B. And then this is same as saying that X less than equal to B and X less than equal to A complement. When you say X is not bigger, less than equal to A means, or it's same as saying that X less than equal to A complement. Complement of this set. Remember, each of these are a set because these are events, therefore they are sets. Therefore, I can talk about complement of those sets. And from set theory, we know that if you have two sets, let's say B intersection with C complement, or let's say B intersection with D, for example, complement, this is same as B minus D. So this is how we define the difference of two sets. B minus D is same as B intersection D complement. This comes from set theory, basics of set theory. So I can write this one as X less than equal to B minus X less than equal to A. So we wrote the event this way. Next, recall that probability of A minus B. In first chapter, we saw that probability that A minus B is same as probability of A minus probability A intersection B. Probability A minus B is PA minus P intersection B. Therefore, here we can say that probability that X is bigger than A, less than equal to B. This is P of, we wrote it this way, so this is like my A minus B. So P of A, that means P of X less than equal to B, minus P of intersection. A minus B is A minus P of intersection. So I need to find the intersection of these two events. So X less than equal to B, intersection with X less than equal to A. Now, what is the intersection of these two sets? See, remember that A is less than B. So if you look at the real line, A, B. So X less than A means this region, X less than B means this region. What is the intersection? The intersection is same as X less than A. So this can be written as P of X less than B minus P of X less than A, less than equal to A. Intersection of these two sets is X less than equal to A, as you can see from this picture. And remember that P of probability of X less than equal to T, we denoted it with capital F of T. So here we have P of X less than equal to B, which is same as capital F of B, minus P of X less than equal to A, which is same as capital F of A. So we show that P of X bigger than A, less than equal to B, is same as capital F of B minus capital F of A. So let's look at an example. In example above, find, let's say, P of X between 1 to 4 with part A using PDFs, part B using CDFs. So with PDF, we know how to use the PDF. We know that probability that X is between two numbers, A and B, is simply same as integral A to B of PDF. So in example above, I mean the example where PDF was given. This example. This example, PDF is given. And we want to find probability that X between 1 to 4, one time using PDF, one time using CDF. Please remember, we already found the value of C in this example. It turned out that C has to be 1. So let me write this formula one more time. So we know f of X equals e to power minus X for X bigger than 0. 0 for x less than 0. So p of x between 1 to 4 is same as integral 1 to 4 f of x dx. Now for x between 1 to 4, because if x between 1 to 4 means x is positive, therefore we have to use this formula here, e to the minus x, so integral 1 to 4 e to power minus x dx. And antiderivative of e to power minus x, we said it's minus e to power minus x, and we have to calculate between 1 to 4. So minus e to power minus 4 minus e to power minus 1. This becomes e to power minus 1 minus e to power minus 4. So this is the answer for calculating this probability using PDFs. Now part B asks us to find this probability, same probability, using CDFs. Now what did we show above? So for part B, P of x between 1 to 4. If you remember, the theorem was telling us that P of x bigger than A less than equal to B is capital F of B minus capital F of A. Here we have P of x bigger than 1 less than 4, but because it's continuous random variable, it doesn't matter. I can say that x between bigger than 1 less than 4 is same as probability that x is bigger than 1 less than equal to 4. Because remember, each individual probability is 0, so I can always add 0 to my probability without changing it. So I can say that P of x bigger than 1 less than 4 is same as P of x bigger than 1 less than equal to 4. And now I can use formula above, or let me say use theorem above, we call it a theorem. If I use the theorem above, then I can write it as capital F of 4 minus capital F of 1. And what was capital F of x? We calculated it in the last example. Capital F of x was 1 minus e to power minus x for x bigger than 0. So for f of 1, capital F of 1 and capital F of 4, both of them, I have to use the second formula here. So it becomes 1 minus e to power minus 4 minus 1 minus e to power minus 1. So this becomes e to power minus 1 minus e to power minus 4, which is same answer that we got in part A using PDFs. So this theorem is another important property of CDFs and helps us to calculate probabilities using CDFs. I want to talk about medians. So definition, let x be a random variable. The pth quantile of this random variable, and here p is between 0 and 1, denoted by phi sub p is the smallest number such that capital F of phi p is bigger than equal to p. Capital F of phi p is bigger than equal to p. So this number is called pth quantile, and another name for pth quantile is 100 times p percentile. And median means 50th percentile. Or phi sub 0.5. So this is how we define phi p. Phi sub p means smallest number where CDF at that point is bigger than or equal to p. Another name for pth quantile is 100 times pth percentile. So if p remember here is a number between 0 and 1. So if p is 0.5, then we have to deal with phi sub 0.5, and that number is called median. So we can denote the median with phi sub 0.5, or we can call it 0.5 quantile, or 100 times 0.5, which means 50, 100 times p percentile, so 50 percentile, another name for median. So median is 5 sub 0.5 or 50th percentile or 0.5 quantile. And this is the general definition for percentiles for any number of p. So let me show you in an example how we can find median or these percentiles. So why don't we look at the previous example that we were looking at, and let's find median in that case. So in example above, find the median and find, let's say, 80th percentile. So again, what do we mean by example above? We mean the example where PDF was given. An example above, PDF or f of x was given as e to power minus x for x bigger than or equal to 0 and 0 for x less than 0. And we showed that the CDF, capital F of x, was 0 for x less than 0 and 1 minus e to power minus x for x bigger than or equal to 0. Now for median, we need capital F of median, because if p is 0.5, then this would be 5 sub 0.5 will be median. So capital F of median should be bigger than or equal to 0.5. And this should be the smallest number with this property. So the median phi sub 0.5 is the smallest number such that capital F of the median becomes bigger than or equal to 0.5. So in this case, the smallest such number would occur if capital F of that number is equal to 0.5. If I find the capital F of a number that gives me 0.5, then if I increase the input, the outputs will be increased as well. And if I decrease that input, the outputs will decrease as well. So if I find, let's say, a number t with f of t equals 0.5, well, that number t satisfies this. And if I have another number, let's say s with s less than t, f of s will be less than 0.5. Let me write down what I just said. See, such number I sub 0.5 can be found by solving capital F of t equals 0.5. Since if s is less than t, then capital F of s will be less than capital F of t, which is 0.5. So that means this number t, the solution of this equation, is the smallest number such that capital F of that number bigger than or equal to 0.5. Because capital F of this number, if it's equal to 0.5, it will be automatically bigger than or equal to 0.5 as well. If a number is equal to 0.5, it will be bigger than or equal to 0.5 as well. So it satisfies this inequality and is the smallest such number, because if I reduce this number t to some number s, then capital F of s will no longer satisfy this inequality. So in this case, in the case of continuous random variable, this seemingly a little bit complicated definition really turns out or can be simplified as saying that capital F of the number equals 0.5 will simply give us the median. Capital F of a number equals 0.5 will give us the median. This bigger than equal mostly can be applied or will be relevant in the case of discrete random variables, because in discrete random variables, this capital F or CDF function can have jumps because it can become discontinuous, so it can have jumps. So maybe 0.5 will not be taken in that case. Capital F, for example, could be 0.4 and then suddenly jump to 0.6. So in that case, I cannot say the solution of capital F of t equals 0.5 because it may have no solution, this equation. If it jumps from 0.4 to 0.6, this equation may have no solution. So therefore, in that case, I really need to work with bigger than equal to, so that if it jumps from 0.4 to 0.6, then I need to consider 0.6 as the smallest output bigger than equal to 0.5 and then find the relevant input. So in the case of continuous case, you can just simply replace this with this condition, which is much easier to work with. Just capital F of t equals 0.5 and then solve for t. That will give you the median. So we want f of t equals 0.5. That means 1 minus e to power minus t equals 0.5. To solve this equation, that means e to power minus t equals 0.5. Take ln. e to the power minus t equals ln 0.5. So that means minus t ln e equals ln 0.5. ln e is 1. So t will be minus ln 0.5. So this is the median. This is for the median. And we also want to find the 80th percentile. 80th percentile means what is the value of p? Because for percentile, the value of p is multiplied with 100. So original value of p must have been 0.8. So for 80th, percentile 100 times p equals 80. So p is equal to 0.8. So we just need to solve for capital F of t equals 0.8. For median, we solve for capital F of t equals 0.5. For 80th percentile, where p is equal to 0.8, we have to simply solve for capital F of t equals 0.8. So that means 1 minus e to the power minus t equals 0.8. So e to the power minus t must be 0.2. Again, take ln e to the power minus t equals ln 0.2. So minus t times ln e equals ln 0.2. And therefore t will be minus ln 0.2. This will be the value of 80th percentile. So this was about medians and percentile. So if I want to explain about what happens here, see, for example, here, this PDF was e to the minus x for x bigger than 0. So it would be a graph like this. And the total area is 1, because we know that the total area under small f is 1. So the total area is 1. Now for the median, means we have to find an input on the x-axis for which the area becomes half, because you want capital F to be half. Capital F means the area function. Remember here we call it CDF, but it's same as the area function, what you called it as area function in math 114. So if you want the area function to be 1/2, means we want an input. In this case, it turned out to be minus ln 0.5. Minus ln 0.5, by the way, same as ln 2, because ln 0.5 means ln 1/2, which is minus ln 2, and then another minus becomes ln 2. So at t equals ln 2, this area here becomes 0.5. The whole area is 1. And at the median, so the median is a point on the x-axis, at which the whole area under the curve becomes half of the total area, which means half of 1, because total area is 1. So up to median, the area is 1, area is half, and then after median, another half, the total area becomes 1. And for example, when for 80th percentile means the number on the x-axis at which the area becomes 0.8 in this case. So again, when we say t equals minus ln 0.2, ln 0.2 means ln 1 over 5, which is minus ln 5. So another minus, so this becomes ln 5. This is same as ln 5. So then at ln 5, at ln 5, this area becomes 0.8 of the total area, which is 0.8 of 1, which is also 0.8. So this ln 5, this input on the x-axis is called 80th percentile, the input for which the total area under the curve becomes 0.8, and ln 2, the input on the x-axis on which the total area under the curve becomes half of the total area, which means 0.5. So this is the interpretation of median and percentiles using graphs of the functions. Now the next topic is about expected values. Expected values. Let's look at how we define expected values in the case of continuous random variables. So the definition and properties are very similar to the case of discrete case. The only important difference is that the sigmas have to be replaced by integrals. The definition, let X be a continuous random variable with, let's say, PDF, small f of X, then the expected value of X, also denoted by mu sub X, is defined as follows. Expected value of X equals integral minus infinity to infinity x f of X dx. Which is also denoted by mu sub X, as we said. So mu sub X equals expected value of X equals this integral. Now, similar to the case of discrete case, this is for expected value of X. If you want expected value of g of X for some function g, so again, let X be a continuous random variable. And let Y equals g of X be another continuous random variable where g of X is an arbitrary function. Then we can say that expected value of g of X is equal to integral minus infinity to infinity g of X times f of X dx. But again, small f of X is the PDF of random variable x. See, everything is very similar to a discrete case, except sigmas have to be replaced by integrals. So in the discrete case, we said that expected value of g of x is equal to sigma g of k times px of k. In the discrete case, we said expected value g of x sigma g of k times p of k. Here we say g of x times f of x. So instead of PMF, we are dealing with PDF. And instead of sigma, we have to replace it by integral. And definition of variance is still similar to before. Definition, let x be a continuous random variable. Then a variance x is defined as expected value of x minus mu squared, where mu is equal to e of x. And again, similar to a discrete case where we had two equivalent formulas for variance, we could have written it this way, or we could have written as expected value x squared minus expected value x the whole squared. So still the same formula is valid in the case of continuous random variables. So again, theorem, let x be a continuous random variable. Then we can say that variance x is equal to expected value x squared minus expected value x the whole squared. And one remark is that the other properties of expected values and variances that we saw in the discrete case are still valid for the continuous case. So all the properties that we have seen before are still valid. So for example, we saw that expected value ax plus b is a times expected value x plus b. We saw that expected value of a constant is same as the original constant. We saw that variance x is bigger than or equal to 0. We saw that variance ax plus b is equal to a squared variance x, and so on. So the proofs, let me leave them as exercise. Because the proofs are very similar to the discrete case. We did the proofs for the discrete case. Still, you can write the same proof. The only thing is that whenever you see a sigma, you have to replace it with an integral. So for example, let's say for expected value ax plus b, this time we have to write integral minus infinity to infinity, ax plus b f of x dx. And then you can write this one as a times integral minus infinity to infinity x f of x dx plus b times integral minus infinity b times integral minus infinity to infinity f of x dx. And then this one, we defined it as expected value of x. This one, we know that it's 1 by properties of PDFs. And therefore, the answer can be written as a times expected value x plus b. So we used the same idea in the case of discrete case. The only difference was that we wrote this was sigma over k, ak plus b. Instead of f of x, we called it p of k in that case. Then again, we could take a out of sigma, b out of sigma. Then we had sigma p of k. We knew it's 1. This time we have integral f. We know it's 1. And instead of sigma k p of k, we have integral x f of x. So very similar. Instead of sigmas, we have integrals here. So I wrote the proof of the first one so that you know how we should work with them. And please make sure you complete the rest as an exercise, the proofs of the remaining properties, which are still the same properties as we saw in the case of discrete case. So let me say proofs because I wrote one proof here. This was proof of e of ax plus b equals a x plus b. So this one we wrote the proof here, but the remaining proofs are proofs of remaining or other properties. Let me leave them as exercise. So if you have learned the concepts of expected values and variances in the previous chapter, here's the same concept, same properties. The only difference for calculation of expected values, instead of finding sigmas, we have to work with integrals. So let me show you in an example how we can find expected value of a given random variable. So again, let me work with the previous example where we already worked with it in through several examples, and we found different features of that random variable. Let me also find the expected value and variance of that random variable. So again, in example above, with f of x equals e to the minus x for x bigger than equal to 0, 0 for x less than 0. Find the average of this random variable, which means e of x, and find the variance of this random variable, which means variance x. So e of x, we know that it's integral x f of x dx from minus infinity to infinity. And here f of x is 0 for x less than 0. So instead of minus infinity to infinity, in this case, in this example, I can write 0 to infinity, because before 0, the function is 0. So I can just say that this integral is same as integral 0 to infinity x f of x dx. And for x bigger than 0, f of x is e to the minus x. So I can write this one as 0 to infinity x times e to the minus x dx. Now I need an antiderivative for x e to the minus x. And how do I find the antiderivative of x e to the minus x? Antiderivative of x e to the minus x can be found using integration by parts. Integration by parts can help me to find the antiderivative of x e to the minus x. How can I do that? Well, integral x e to the minus x dx, I can call this one u and this one dv. So if I call u as x, dv as e to the minus x dx, so that means v should be minus e to the minus x. If dv is e to the minus x dx, v should be antiderivative of this, which is minus e to the minus x. And du is same as dx. So integral x e to the minus x dx is same as integral u dv. Integral u dv, we know it's uv minus integral v du. So then this will be x times minus e to the minus x, uv minus integral v du. So minus e to the minus x du means dx. So then this will be x e to the minus x minus x e to the minus x plus integral e to the minus x dx. And then this is minus x e to the minus x minus e to the minus x. I can say plus c here because it's indefinite integral. And for definite integral, integral 0 to infinity x e to the minus x dx, I can say that this is the antiderivative, so I have to calculate this between 0 to infinity. So then this will be limit t goes to infinity, this function minus x e to the minus x minus e to the minus x, and then calculate it between 0 and t. Integral 0 to infinity is same as integral 0 to t, and then let t go to infinity. So I have to calculate this one, the antiderivative of this function, which is this function between 0 to t, and then let t go to infinity. So at infinity, so this becomes, let's calculate this limit. So this will be minus limit t goes to infinity. If I replace x with t, becomes t over e to power t. If we replace x with t, becomes t times e to power minus t, which is same as t over e to power t. And then there's minus in front. And this one, if I replace t, x with t, becomes minus limit e to power minus t, t goes to infinity. And then I need to replace with 0. At 0, this becomes 0, and this becomes e to power 0, which is 1. So minus e to power minus 0. Now for this one, we know that e to power minus infinity, it's 0. So this term, middle term, is 0. This term here, e to power 0 is 1. There is 2 minus in front, which they cancel out. So this becomes plus 1. And finally, this term here, this term as t goes to infinity, this becomes infinity over e to power infinity, which means infinity over infinity. Infinity over infinity is indeterminate, but we can use L'Hopital to calculate the limit. So by L'Hopital's rule, we can write this one as limit. L'Hopital says limit infinity over infinity. We can differentiate top over differentiate bottom. Derivative of top over derivative of bottom. So limit derivative of t is 1 over derivative of e to power t is e to power t. T goes to infinity. So this will be 1 over infinity, 1 over e to power infinity, which is 1 over infinity, and that's 0. So we calculated each of these 3 terms. First term is 0. Second term is also 0. Next term is plus 1. So 0 plus 0 plus 1. The answer is plus 1, or just 1. So we showed mu equals e of x equals 1. So in this case, the average is also 1. Now the question was asking us to find the average and to find the variance. So I found the average for you for the variance. I can leave it as exercise. So finding the exercise, find variance x. But let me give you a hint. But we know that variance x is expected value x squared minus expected value x the whole squared. Expected value x we already calculated above, so this is expected value x squared minus 1 squared, and that's expected value x squared minus 1. And expected value x squared, we just need the expected value x squared. How do we calculate expected value x squared? Well, we know that expected value g of x can be found using this theorem. Expected value g of x, in the case of continuous case, integral g of x times f of x dx. So integral, in this case, g of x is x squared. So integral minus infinity to infinity, x squared times f of x dx. And if you remember, f of x is 0 for x less than 0. So instead of minus infinity to infinity, I can just say 0 to infinity and replace f of x with e to the minus x. So I'll be left with integral 0 to infinity x squared times e to the minus x dx. And then the rest is just calculating this integral. Complete the calculation. So again, you need an antiderivative of this function. And antiderivative of this function, again, can be done using integration by parts. But this time you have to apply integration by parts twice. Because previous case, we had x e to the minus x. We can apply the integration by parts once, and we found the antiderivative. This time you have x squared times e to the minus x. So you have to apply the integration by parts twice to find the antiderivative. Once you find the antiderivative, then just apply the limits 0 to t, and then let t go to infinity. Find the limit similar to what we did for e of x. Find the limit, and then this way you will find e of x squared. Once you find e of x squared, variance x will be in this case e of x squared minus 1. Okay, guys, so that's all for today. Thank you, and see you next time.